Well then, welcome this afternoon to another section of 8813, our special topics course on wireless without batteries. This transmission of wireless power and transmission of information with minimal expended power. Two similar topics that actually have a lot in common to one another. So we've had two lectures so far. Your first lecture was just an introduction to the topic and kind of motivation. What are the trends that is making this particular topic important to study and why it's interesting? What are the trends in electronics and communications? Some of the possible uses of it, I think we talked a little bit about. And then we talked some about in the next class period, we talked about some basics of energy harvesting. Yeah, how do we deal with antennas and circuits? That's sort of the general topic. We had a lot of examples out of the energy harvesting world. We talk a little bit about what are the circuits that you hook to antennas that you harvest with. And we worked maybe an example problem or two, and I think you've got an example problem in your homework that's very similar that you can practice on. You know, my philosophy of the homeworks is always that they're really good. They're important to stay abreast of, but it's most important just for you to learn the topic. So if you get stuff wrong on the homework, first of all, I give a lot of partial credit. Secondly, it's better to get it wrong on the homework than it is on a test, right? Counts for less. Counts for less wrong. And I'll be updating the reading materials. I was trying to do that before class, but T-Square and I, and the Chinese export bandwidth and I are all having a fight this afternoon. But look for something later this afternoon posted. Today's topic, we were technically supposed to have a class period on Friday, but I assigned about 3 different YouTube videos. I just wanted you to get familiar with the background of radio wave propagation, because it's important for what we do today, which is the link budget. I'm not going to make you do any upside down triangle calculus, as I like to call it, involving the wave equation. Those lectures came out of my undergraduate EMAG class and my undergraduate antennas class. So I make my undergraduates do this. So in all rights, I should ask you to do this stuff, right? But we've got other important things to do. Most of you have seen that as part of your undergraduate. We just need to be able to talk about it, because we're going to be talking about how radio waves travel from one point to another. They'll look like spherical waves or plane waves. We'll need to deal with polarization, and at times we'll need to get down there and discuss the field theory of why things are going. So I want you to have that background. Most of today's discussion, however, will be with respect to power, because ultimately, outside of nitty-gritty RF engineering and electromagnetics, that's what the rest of the world is most interested in. How much power am I getting from point A to point B? Because in a way, that's kind of the showstopper in what we want to do, both in terms of collecting energy and collecting data for communications. There's a famous theoretical limit called the Shannon channel capacity theorem, and in a Gaussian white noise channel, Claude Shannon years and years and years ago, back in the 1940s, predicted that there is a fundamental limit to how many bits per second you can send through a channel that has your normal background noise in it. And that fundamental limit is a function of bandwidth and power, and that's it. So it doesn't matter what fancy modulation scheme that you're using. In a way, all these modulation schemes are essentially trying to get to that particular limit for that channel. And so that's one of the many motivating factors for why predicting how much power to get from one point to another is an important topic. Homework assignment 1 is already online. If you've seen it, it'll be due this Friday. It's a very straightforward set of assignments about energy, one little exercise about energy harvesting, and another one about antennas and circuits that you can take a look at. I wanted to get that off, get a real simple homework assignment, and probably another one before the Chinese New Year break commences. And that way you can go into Chinese New Year free of assignments. You don't have to worry about anything. I won't have anything due like the day everybody gets back, right? That would be low. mean. Okay. And then of course for the distance learning students, that assignment will be due 1 week from this Friday. You can hand it in on Friday, but you have a week-long window to do it. Okay. Any questions before we get into today's lecture? About the class, about past material, about life? None? Okay. Let's go. So I've actually, every lecture class period, I assign a lecture, or I assign a reading, like from a IEEE paper or something like that. I've got actually 2 readings for today. One of them is by, let me get the right font here. Wireless Communications. It's an excerpt from a book. Wireless Communications, Principles and Practice by Ted Rappaport. It's the section on path loss modeling. It might not have hit T-square yet. I was in the middle of uploading it before I came up here. So I just took some excerpts from his book. I'm sure he doesn't mind. He's my graduate advisor, so I can plagiarize the heck out of him or violate his copyright, and he probably doesn't care. Of course, all the stuff that I put on the T-Square site is for your consumption only. Don't put it on the web or post it to WeChat or whatever, because that would be a violation of the copyright. I'm abusing, in the US we call it the fair use copyright material, right? If I'm an educator and I'm not charging you for it directly, right? I can provide you with an excerpt from these readings. So that's number 1. That talks about regular link budgets. And then number 2, I have an excerpt by paper by Nikitin and Rao about RFID link budgets. Kind of interesting. So go ahead and look through them and get a familiar what we're talking about. This is more conventional link budgets, which I'll focus on mostly today, but we'll talk about these as well, at least mention them. And then we'll do a more exhaustive treatment of them in a later lecture. This first one is where you just send power from one antenna to another. We're going to fill in the missing gap in the one thing that we learned last week. We learned basically how to deal with power and how to track it from a transmitter to a receiver, from at least the transmitter to the transmit antenna. How do you get power from here to here? How do you get power from here to here? We haven't mentioned how to calculate power from here to here. And this will sort of complete the whole analysis. Once we understand that, then we do a lot of fun stuff in applications and the like. Okay. Now, so today's topic is link budgets. We'll break in about a half an hour, and we'll take about a 15-minute stretch break, and then come back. Okay. Now, there are 3 types of link budgets that I'll talk about today. The first one is the conventional link budget. And that's where I have power at A, and I want to transmit it wirelessly to point B. Straightforward enough. Then we'll mention also the radar link budget. And the radar link budget tells you how to get power from A to object B to object C? Basically, what if there's a stopover? So you have to reflect off of something or scatter off of something. That's interesting. That's all. You know, there are entire courses at Georgia Tech in the main campus dedicated to radar and signal processing. We're going to touch upon it just briefly because it's an interesting technique. However, there's another method that we're going to look at, and this is called backscatter communications, which is how a lot of low-powered sensors work. And this is A to B with information to C. And in both cases, case number 2 and case number 3, A and C could be the same location, and often is. We'll review the terminology for talking about that. It's really where is the information originating from, which determines which of these link budgets you use. In a classical conventional link budget for radio communications, up here number 1, the information is going from A to B. It's kind of coming in at A and then you're transmitting it to B. In the radar link budget, the information is really the existence of the scatterer. Can't spell today. It's the presence of scattering B. And so the information is really part of the environment. In number 3, the information is actually coming in through node B. Node B is actually adding information. And then it's making its way back to a remote location. So that's sort of the big picture of what we're studying today. So let's start with our link budget. And there'll be a slightly different treatment if you're wondering on my YouTube channel. I think WAV04 is the link budget lecture that I give in my satellite communications class. It'll bear some similarities with today's lecture, but I'm going to emphasize different things. However, if you want to go back and kind of, you know, I think I mentioned this in my first period class, as a teaching philosophy, you have to see something 3 times before you understand it, right? You don't ever really understand something. You just get comfortable with the idea. That's my philosophy. That's why it takes 3 times. You know, your brain is not a computer. I don't have a bunch of information that I just need to cram into your memory circuits. And then you go from binary, not understanding, to understanding. You know, we work very differently as human beings from that. So if you want some background information, like another perspective, that might be a good place to look at it. Okay, so conventional link budget. Our starting point for link budgets is always something called the Friss free space equation. This guy, Friss, was a Dane. He was from Denmark. And so I've been told by Danish people that the proper pronunciation of his name is actually the Frege free space equation. Frege. That's Danish, apparently. Most of the people I know say Fries, the Friss, because they're not Danish. Although I've also heard people from all over the world pronounce this all sorts of different ways. I met an Australian professor once that called this the Fry equation. Or some people call this the Free equation. They try to turn it into a French name, I guess. And so there's no agreed upon way to say that word I've found in years and years working in radio propagation. Even the veterans don't agree on how to do it. So I prefer freeze, but apparently freeze is probably even more accurate. But I don't know anybody that actually has ever called it that in my profession. So that just goes to show you. The problem with short names, you know, in my SATCOM class we have this one, we talk about error correction coding, and one common block code is this Bose Hakwangem Chowdhury code. It's 3 Indian people, I think. And of course nobody can say Bose Hakwangem Chowdhury, and it's a kind of a mouthful, so people just call it BCH. This guy has the unfortunate, it looks deceptively easy to pronounce, and so nobody's going to ever abbreviate the equation. So what is the Frisch free space equation? All that to say, Frisch free space equation says if I have a certain amount of power into an ideal antenna, here's my transmit antenna, the bent coat hanger, P sub T, and these guys are separated by a distance r. How much power comes out of this P sub r? So I'm just going to go ahead and write the equation down. We won't derive anything at this point. Receive power, Frisch says, is P sub T times a unitless factor called the gain of my transmit antenna. This is unitless, and so is the gain of the receiver antenna in the direction that the wave is traveling. These can be functions of orientation. Which direction is the radiation leaving the antenna? Which direction is the radiation arriving from the antenna? And then I have lambda squared, that's wavelength of radiation, over 4 pi, the distance quantity raised to the second power. So lambda, wavelength in free space, in meters. So that's, of course, the speed of light divided by the frequency. P sub T is transmit power, usually in watts. P sub R is receive power. It's going to be the same units as whatever transmit power is. R is transmit receive separation distance. And then we've got these two transmit or receive antenna gain. And that's it. That's the Frisch free space equation. It's named after a physicist who formulated this. And there are a couple big assumptions in here. First of all, this is free space, lossless free space. I don't have any additional losses. I don't have any blockages. I don't have any scatterers scattering additional power. This is the ideal radio link. You can think the best way to get this scenario is to put your transmitter and receiver in outer space. We can approximate some earthbound and a lot of satellite links with this equation, but it is very idealized. We're going to add some realism to this in this lecture, and then as we go on, as we need it, we're going to add some more realism as well, especially when we talk about some small scale fading, which will be interesting. Okay. Any questions so far? Now, that's the first free space equation. That's the linear form. In RF engineering, as we discussed earlier, what do we use when we talk about power? We don't rarely use watts in this class. What do we actually use? DBMs. DBMs or DBWs. We like logarithmic scale because the things that we're dealing with are so disparate in their orders of magnitude. And the link budget is no exception. When we start with the Friss free space equation, we like to convert that to a logarithmic form to make it a little more convenient. So you'll also see this expressed as the logarithmic link budget equation, which is just the logarithmic form of the Friss free space equation, and sometimes with extra terms added on to it to account for different losses or gains. So if I take 10 log base 10, both sides here, what do I get? Well, here I've got P sub r, and that could be in either dBms or dBws. Whatever you start on the left-hand side, you got to have on the right-hand side. So if I could actually make this all work out in dBms, I just got to make sure both P sub t and P sub r in the logarithmic link budget are both dBms. Don't mix and match those. Then, okay, I take 10 log base 10, all this stuff on the right-hand side. So the nice thing about logarithms is that everything that gets multiplied together really gets added. In fact, that's why it's called a budget, because it makes RF calculations look more like adding up a row of numbers in your checkbook rather than multiplying. And so I've got a PT added into my equation. That's going to be either dBms or dBws. Make sure there's a correspondence either way that you do it. And then I'm going to add G sub t. Except this is no longer in a unitless value. When you report this, this is 10 log base 10, the gain pattern. Yeah. So this is going to be dB, and then we put a little I next to it. That's decibels with respect to isotropic radiation. Because if you go back to the field lectures that you looked at, we calculated something like a pointing vector, SAAV. Do you remember that part? A pointing vector. What units does that have? It's sort of a power density. Watts per meter squared. Perfect, perfect. So if I took the magnitude of that, I should get something, the radiation power density in a particular direction, and it will have units of watts per meter squared. Now, if I have an isotropic radiator, let's call this S iso. What is the word isotropic? That was another vocabulary word that came out of those first 3 background lectures on radiation. What does that mean? Same in all directions. Iso means the same in Latin. Trope means side, I believe. Yeah. Oh, good. We have a good Latin scholar here. And so, same in all sides. So if I'm starting out with the same P sub t up here, and I'm transmitting it equally in all directions, what would be the power density in watts per square meter if that power was spread out across a sphere of radius r? So if I have a sphere of radius r, what's the surface area of that sphere? 4 pi r squared. 4 pi r squared. So this would be the ideal isotropic radiator. This is the actual radiation you do get from your antenna, the radiation power. The ratio of these two, that's actually how we define gain, at least from a transmission perspective, right? We say I put P sub t into an antenna, I go a certain distance in the far field away, I measure the power density. How does that compare to what in a theoretical isotropic radiator should be? And you notice that that's a very empirical way to determine it, right? I'm physically putting power into an antenna, I make the measurement, and then I compare it to the isotropic radiator. That's gain. It's different from another quantity in antenna engineering that we call directivity, which is similar, but you'll notice if I do it in this empirical fashion, I'm also accounting for radiation inefficiencies. Because it turns out that power that you put into the antenna does not always make it into a radiated wave. Sometimes there are ohmic losses on the surface of the metal antenna that absorb power. Sometimes there are dielectric losses in the immediate area of the antenna. If it's, for example, if you have a patch antenna, I don't know if you know what that is. It's a piece of metal, usually a rectangular hunk of metal that's radiating. It's on a printed circuit board, which means it's got a ground plane and some FR4 dielectric material underneath of it. That FR4 dielectric material, especially when you get up to upper UHF microwave frequencies, starts to get lossy, and you can burn up energy on that so that the power that you put in doesn't all make it out into radiated waves. So that's an important concept in antenna engineering, the difference between directivity, which is sort of like this calculation. Think of it as this calculation, the ratio of actual radiated power to isotropic radiated power. If the antenna was lossless, radiation efficiency of 100%, we would say. And then this idea of gain, which is really directivity times radiation efficiency. That's how it's formally defined in antenna engineering. That's the realistic factor, takes into account actual losses of the physical antenna. At UHF frequencies are lower, we're talking like less than 3 gigahertz. If it's a halfway decent antenna, you can almost approximate gain as equal to directivity. If it's a well-made antenna, that should be the case. You'll be lucky to, you'd be unlucky to lose more than 20% of your power. It's possible to make a worse antenna, I suppose, but that's a good start anyway. As you go higher and higher in frequency, because the ohmic losses and the dielectric losses, whatever you make your antenna out of, becomes lossier, it becomes more and more difficult to make that approximate equivalence. If I give you an idealized problem in this class, you can almost always assume that directivity is equal to gain unless I tell you otherwise. Or at least you can approximate it. It's never equal, right? So anyway, you've got two of those factors, gain of the transmitter and gain of the receiver. That's also in dBi, decibels with respect to isotropic. And then you've got two more terms. So in classical propagation theory, what we do is we take 10 log base 10 pi squared over 4 pi squared, or we just write that as 20 log base 10 pi over 4 pi. And then we'd have minus 10 log base 10 1 over r squared, or if you want to write it minus 20 log. Great. Everybody understands their logarithmic math. We don't have to review that. That's fantastic. And we like to break it apart in this fashion because this has a special name. We call this path loss at 1 meter free space. The idea is that if you set r equal to 1, what's log 10 of 1? 0. Yeah, 0. So that term goes away. And so basically, you got your transmit power here. You've got two unitless or dBi gain values. Any real loss at 1 meters is due to this term here. And this term is also where all the frequency, the main frequency dependence comes in, right? This is lambda. Lambda is speed of light over frequency. So really, that's where the frequency dependence of the link happens. This term over here is the path loss with respect to 1 meter free space. And this is the part where you have to model. If you've got some additional losses, we'll talk about ways of modeling that. In fact, we can even add that to the path loss the link budget equation, additional losses after this term. I won't illustrate it here, but instead I'll just show the direct translation from the Friss free space equation. Okay, so let me write the clean version of this on the next slide. We have P sub r is P sub t plus G sub t plus G sub r plus 20 log base 10 lambda over 4 pi. You can spend a couple of weeks just talking about this beautiful equation. The bedrock of radio communications. Because there's a lot of interesting behavior here and a lot of nuances that a mature field like RF engineering, if you're going to do a little bit of RF engineering, there's some things about this that you should know about in the way that RF engineers like to talk about this equation and keep track of things. The first thing is that some RF engineers like to lump these two together into a term that they call effective isotropic radiated power. EIRP. Effective isotropic radiated power. And that's reported in the same units as you're trying to calculate either dBWs, decibel milliwatts, or dBMs, decibel milliwatts. And this is sort of right, like it's not a physical power. It's if this were an isotropic radiator, how much power would you have to put into it to radiate the same as this transmitter in this particular direction? So you got transmitter radiating in a particular direction. Quite often this number seems a lot bigger than it should be, right? Because for example, in America, we have FM radio transmitters, just like here. And the station engineer that kind of oversees the electronics and makes sure the transmitter is running okay, they usually like to work in EIRP because it makes their transmitter sound more impressive, right? So for example, at Georgia Tech campus, there's a campus radio station. It's called WREK. And when they were transmitting, they don't transmit this much power on their digital channel, but when they were transmitting purely analog, they'd transmit maybe, I'd say, 10 kilowatts into their antenna. I said, that sounds like a lot of power. Well, not really. It's like 100 light bulbs, the old 100-watt incandescent light bulbs. You're illuminating 100 square miles or more, hundreds of square miles when you cover an area. 10 kilowatts is actually not that much when you think about it, when you're blanketing power all over that area for communications. It's like 100 light bulbs. But when they go to report, they say, well, they've also got a transmit antenna. It's an array of circularly polarized kind of bent dipoles that they use. And collectively, you're getting a lot of gain at the horizon. Maybe, let's say 10 dBi. I think they get a little bit more, maybe like 11 or 12 dBi on their realistic tower. But the point is that that's a factor of 10 in the linear scale, at least, going to the horizon. Now keep in mind, this antenna does not radiate that efficiently every direction, right? It's really only at the horizon. It's focusing power in the horizon and it's taking it away from the other regions of space. Because at the end of the day, an antenna is just a hunk of metal. It doesn't really amplify anything. It doesn't have a gain in the same way that an amplifier has a gain. It's just more efficiently focusing power in some directions at the expense of other directions. So the interesting thing is, like, when the radio station, and I'm not accusing WREK of doing this, everyone does this. They'll be like, okay, I'm transmitting at 10 kilowatts of power, but I've got 10 dBi at transmitting. So my EIRP is really 100 kilowatts, right? And so there are even some radio stations that transmit a lot more than WREK, the Georgia Tech radio station. They maybe transmit 50 kilowatts, and they got a 13 dBi antenna, which means they really got a megawatt EIRP. And so they come on when they announce their call signs, like between playing music or in a commercial break, they say, "This is WREK W such and such and such, transmitting over Atlanta at 1 megawatt of power. It sounds really impressive, right? Like, oh my goodness, maybe I should wear an aluminum foil suit when I walk around outside. It's really not that much because they're just using EIRP because it sounds more impressive than just using P sub T or G sub T. Okay. So that's one thing to know. We will be talking about EIRPs in many instances. There's another question. We said that G sub T could be defined as the actual average pointing vector over the isotropic pointing vector, the power ideally distributed over 4 pi stereoradians. That is a transmitter perspective, right? What about receiver? How do you define gain at a receiver antenna? So one way that I like to think of a receiver antenna, you studied the plane wave. And I think in that video you did a calculation of what is the pointing vector of a plane wave. The reason why they call it a uniform plane wave, for example, is that really the power density across the uniform plane wave is the same no matter what, right? It's the same watts per meter squared. And truthfully, all of the waves that we talk about in this class are going to be realistic waves that start from point sources, right? However, if you go far enough away from the point source, eventually the radius of curvature of that circular wave, close in, if you're just looking at kind of a local area, it looks like a plane wave, right? And so that's why that lecture on plane waves is so valuable as a background material, because at the end of the day, everything realistic is a plane wave when you're in the far field. So one way to view a receiver antenna is like a cookie cutter in space. You've got this plane wave in space, and it has uniform density, uniform watts per meter squared, as we calculated in that lecture. And you can think of this antenna, it's a device that converts a plane wave to a voltage. It takes power out of the plane wave and puts it at a voltage at the terminals of whatever you connect the antenna to. How much power does it take out of the plane wave? Well, it depends on how big the cookie cutter is, how big the cross-sectional area. We say an antenna has an electromagnetic aperture. We measure it in meters squared. It's an area over which it approximately gathers power. Where the analogy tends to fall apart is, truthfully, antennas don't cast sharp shadows, right? The way I'm presenting it here, it sounds like I've got an electromagnetic aperture. It's a cookie cutter. You know, maybe it's circle shaped, and it sucks a circular amount of power out of the plane wave and converts that. And then you think, well, if I got behind that antenna, I should see like a perfect disk cut out of the plane wave. Well, first of all, Maxwell's equations doesn't like sharp corners in its field solution. In fact, one of the ways to view Maxwell's equations, it's almost like a low-pass filter in free space. It smooths over all the differences in wobbling, in oscillating propagation. The lower the frequency, the more the smoothing. So when we say an antenna has an aperture over which it gathers power, it's okay to approximate it as an actual physical aperture, but recognize that the edges are going to be fuzzy. It's not like it gathers 100% of this power from the plane wave, and then when you get beyond the edge of the aperture, it gathers 0%. There's a little tapering and some oscillations that go on along the fringe. Studying the exact solution of a plane wave washing over even the simplest antenna takes about a month of ECE 6350, a great graduate level class, which we almost never offer on video, which is kind of a shame. Maybe I should try to lobby my electromagnetics TIG group back at Georgia Tech to do that, because I think that would be interesting for people outside of the Atlanta campus to take. It's a good just background radiation electromagnetic theory class. Yeah?
For this one, is also logarithm?
Oh, no, this is the linear definition. I should be very careful. I'm glad you brought that up, because the way I've written it here, this is in the dBi scale. Whenever I deal with a physical quantity, whenever I go into E's and H's and S's and all that stuff, this is in linear.
why it doesn't have a logarithm?
So this is the physical definition, and whenever you have a physical definition, it's always in linear units. The logarithmic definition is a convenience way that RF engineers like to deal with antenna gains and powers. So you would have to take 10 log base 10 of this quantity to get it in there. If there's ever, don't be embarrassed, like I'm going to be throwing around antenna gains and things like that. If there's ever any doubt, just ask me, is this linear or logarithmic? That's a really important question because it's a big difference between 10 dB, that's a terrible example. There's a big difference between a 40 dBi antenna and a 40 linear gain antenna, right? 40 linear gain antenna is only 16 dBi in the logarithmic scale. So you get very wrong answers if you start confusing those quantities. I liken it to the difference between degrees and radians, right? Most of your physical formulas and natural formulas are all defined in terms of radians, right? Any math formula involving a cosine or a circle, or but we report in degrees because everybody has trouble thinking in radians. I say, oh yeah, look at that thing, that arc is 1.8 radians long. No idea what that means. But if I say, oh, it's 110 degrees, oh, okay, yeah, a little past 90, I got it. So same thing. dBs, dBis, dBms, that's like the degrees. None of the physics actually works out in that scale, but it's a very convenient way to report the number. Whereas radians are like the natural linear units in the first free space equation. That's how you do all your calculations. It's only for reporting convenience when you're trying to grasp, well, how much is this power? How big of an effect will this actually have? Okay, so all that to say, okay, here's how we define gain. The way that we define gain from a receiver perspective, here's another really good formula to have. 4 pi, the effective electromagnetic aperture, this is units of meters squared. Again, this gain formula is in the linear scale, divided by lambda squared. So the bigger the aperture and or the smaller the wavelength of radiation, the bigger my gain will be as a receiver. And it's one of the most fascinating consequences of physics that defining your transmitter and receiver antenna gains in this faction, if you use this on the same antenna in the same direction, you'll get the same number. These are the same. By reciprocity, this fundamental principle in electromagnetic radiation, it turns out that defining transmitter gain like this gives you the same number as defining the receiver antenna in this fashion, as long as they're the same antenna in the same physical scenario. So that's a very interesting consequence that you should always keep in mind. So, that's why they only really, on any antenna spec sheet that you download from the internet, they only report one gain because it's the same whether you use it as a transmitter and a receiver. That simplifies things greatly. One other thing to mention too about antenna gains before we get into some other aspects of the link budget equation. How people report antennas can change a lot. So G sub t, both G sub t and G sub r are like this. We said that this takes into account both directivity and radiation efficiency. In our physical modeling of a radio link, remember we had a source power and then a load power. What else were we taking into account in that physical link that I have not listed here? There was some other loss in the system when we were studying antennas as circuits that could occur at this junction. What do we call that loss? Yeah, mismatch loss. Like if I've not properly matched the circuit. So now, from your perspective as students, you can do now everything, right? What we called P sub S, we calculated early on what was the mismatch loss in a circuit last week to get to the actual transmitted power, right? Because P sub T is not necessarily the power that I've put into the device, because some of that power reflects off if there's an impedance mismatch. And the same goes from here. There's a received power, P sub R, and not all of it makes it to the load because there might be a mismatch. It might reflect back out of the antenna. And now I'm telling you that there's a way to go from PT to P sub R. That's the first free space equation. So now you have the ability to do the entire system. I put P sub source in. I get P sub L out. I can account for the directivity, the radiation efficiency, and the mismatch loss. And in the standard IEEE, there's this thing called the IEEE Antennas and Wave Propagation Standards Committee. This is a committee that meets once or twice a year, has been doing it for decades, and they decide how to define the official terms to talk about things like RF engineering, wave propagation antennas. And their definition of gain, just pure gain, absolute gain is sometimes what they call it. They'll just call it gain, or sometimes absolute gain. Those, when they do that, they're talking about a definition of gain that includes these two components. You have to be careful because in some papers and some specifications specifically, if you get a specification sheet off the internet for an antenna, sometimes what they're talking about is what the IEEE defines as realized gain. And realized gain, just to clarify, usually assumes that you've got a standard impedance, 50 ohms, into the input of an antenna. And in this case, G sub T includes mismatch losses, in addition to directivities and radiation efficiencies. So for example, if this antenna is only slightly matched to 50 ohms, maybe the actual impedance is 80 ohms. They tried the best they could to match it, but it's got a little bit of residual reflection at the frequency that they want you to operate it at. Well, in this case, G sub T would have the directivity, any of the ohmic losses and dielectric losses and inefficiencies and radiation, and then they will have included what we defined as the mismatch loss factor last week into their gain. That should be called realized gain, but most people never actually call it that. They just call it gain on a specification sheet. So just be aware that that may include losses in addition to what we are going to be. I mean, I like to specify it. This is realized gain. You know, that should be only directivity times radiation efficiency. Okay, any questions so far? Oh, yes.
This realized gain is including the losses?
The realized gain includes the mismatch losses, yes. In addition to directivity and radiation efficiency. So there's 3 phenomenon instead of 2 phenomenon. So you think of it, directivity is the purest physical result. This is like the physics result. Radiation efficiency, when you add that in, that's just putting some practical engineering into your metric. And then sometimes it's just plain lazy when you add this other thing. It includes mismatch losses. If you do that, you're supposed to call it realized gain. Just be aware that some people do not. In this class, if you're not given any electrical specifications about the circuit that antennas are connected to, you can assume that the mismatch losses are negligible. Thus, realized gain is the same as absolute gain. But you have enough savvy in this class that you can calculate both scenarios if that's the case. Okay, I'm a couple minutes over my break period, so I'm just gonna pause here. Let's go back in about 10 minutes. Okay, we're back. So, now everybody's an expert at classical link budgets, right? Now let's talk about something different, the radar range equations, or just radar equations, what we often call it in wave propagation. And to understand a radar, first of all, we're going to do an example of a monostatic radar. Monostatic, that's a fancy word for the transmitter and the receiver are in the same location. In some cases, the same antenna. You send a wave out, you strike an object, and that object radiates part of the power back to here. We're separated by a distance r. And let's pretend for a second that that object actually is an antenna. Right? Let's say we were using the classical Friss free space equation. Now remember what we said receiver gain could be defined as. It's 4 pi times the effective electromagnetic aperture over the wavelength squared. So if I plug this term into the classical Friss free space equation, then what I get is PR is equal to PT times my GT. Remember, these two together can be considered EIRP in the linear scale, times 4 pi electromagnetic aperture lambda squared over, let's do it separated out, 4 pi squared times r squared. So you see, automatically one of these 4 pi's cancel. And I got a lambda squared in the denominator too. That should cancel, right? And I'm going to go ahead and divide through by electromagnetic aperture. So what I really have is received power divided by the effective electromagnetic aperture. And this looks a lot like the magnitude of Poynting vector, doesn't it? It has units of watts per meter squared. You can think of it actually as the amount of power I have washing over my antenna. We say, well, that's equal to my EIRP times my transmit power times my antenna gain divided by 4 pi r squared. And that's the one-way link budget. You're going from point A to B. Now, if B is not a communications antenna, but rather just an object that's going to reflect power, one way that we treat that in electromagnetics as simply an object with some sort of physical area that grabs power from here and transmits it back out, right? So if you think about it, a radar link, especially this monostatic one I'm drawing here, you can think of it as an antenna here, B at point B, that almost has two link budgets glued together. That antenna absorbs power and then reflects it back. This should have 1 over r squared losses this way. This should have the same 1 over r squared losses in the other direction. The area over which I gather and then re-radiate power is this thing called radar cross-section, sigma RCS. RCS stands for radar cross-section. It has units of meters squared. And if you take this pointing vector over here, this guy here, and multiply by sigma RCS, you can think of this as the, quote, transmit power for the second leg of the link. So if I conceptualize the link in that terms, then my actual received power back at the radar receiver is really my transmit power, which I said was SAV times sigma RCS times the receiver antenna gain lambda squared over 4 pi r squared, right? This is effectively taking the place of the transmit power in that leg back. And then of course we have an expression for this guy already, right? This guy is what I originally transmitted over here, PT. It had a 4 pi in the denominator, so I can now raise this up to the third power. It had an r squared in the denominator, so this is now r to the fourth. There's a GT, a GR, a lambda squared, and a sigma RCS. And this is my radar equation. This is the equation that you use at the airport when you've got a spinning dish antenna turning around to figure out where is the plane, how strong is the return, and what is the time lag between when I transmitted a radar pulse and when it came back to me. You look at the signal strength to see if you've got the fidelity to detect it, and then you look at a time lag to see if you could figure out how many kilometers out is my target. Okay. And this is a useful equation. We're not actually going to do much with this equation because this is not how you transmit information. The first way and the third way that we're going to talk about. But this is a nice intermediary for understanding the importance of backscatter communications and how to analyze that type of system. It's also a really interesting equation to look at to figure out the frequency dependencies of the link budget, right? So in my original link budget, my first free space equation, the linear form, let me go ahead and write that. Okay. The Friss free space equation. Is it better to transmit at higher or lower frequencies? Remember, lambda has a 1 over f dependency. So does my link get lossier at higher frequencies or lower frequencies, just according to the Friss free space equation? Lower is better, right? Yeah, that's right. That's particularly true when you don't have the freedom to get big gains here, especially when you're at lower frequencies. So for example, if I have a transmitter, let's say it's an AM or an FM transmitter, and I'm radiating power all along the horizon. I don't know where I'm broadcasting something, so I don't know where my users are. I could have a lot of users and they could be in every direction. So by definition, I can't have a really big gain because that would imply that I'm focusing power in just one direction. So I have to have a gain probably close to 1 in some instances. I mean, I can make approximations, say, well, most of the users are on the horizon, so maybe I can get gain that way. But especially at the user terminal, if I'm receiving a signal, I don't know where the signal's coming from. I could have if it's a mobile phone, I could be here, I could be here, I could be here, I could be looking up, I could be turning this way. I have no idea a priori where the signal is coming from. So by necessity, any mobile phone antenna is going to have a really low gain, usually no better than 1 or 0 dBi. And the transmitter gain is not going to be much better in low frequency transmission applications anyway, especially when you get down to like AM radio where the wavelength is much bigger than your antenna. You can only make a very low gain antenna with a small amount of metal compared to the wavelength. So from that perspective, low frequency is always better because according to the Friis free space equation, I got a lambda squared in the numerator, which is effectively like having a lambda squared in the denominator. Now that's not necessarily true if I have the freedom to point an antenna, right? So for example, if my receiver antenna had a fixed aperture, let's say I have this much real estate to build an antenna, and I know where to point it. Look what happens to the math here. Oh yeah, get this dang screen out of the way, hold on. Whoa, turn into little. I gotta inch this thing down. Okay, just to get to a new tab. Okay, there we go. So, remember we said that at a receiver, my gain is 4 pi, the physical area, electromagnetic area. If you have more physical area, you get more, you're gonna get a bigger cookie cutter, right? So generally, the bigger your antenna, the more directional you can make it, the more aperture you can pull energy out of. That means you're gonna have to point it, because you're gonna get gain whether you want it or not in that particular direction. And if I plug that into my Friis free space equation, I get this. PT, GT, 4 pi r quantity squared. I got a lambda squared in the numerator, lambda squared in the denominator that cancel, and I have this electromagnetic aperture in meters squared. So think of this as a broadcast to directional link. Okay. Now how about this link? Where's the frequency dependence? What's it better to transmit at? Higher frequency or lower frequency in this link? It's a trick question. There is no frequency dependence. That is, if I am only concerned about exchanging electromagnetic energy between 2 points in space, if I have a fixed amount of aperture and I have the freedom to point it somewhere, it doesn't matter what frequency I use. Now there are other secondary considerations too, right? Generally speaking, electronics at higher frequencies are a little lossier. They get progressively more lossier, right? Cables get lossier, amplifiers get lossier, everything. So there might be some secondary considerations. But generally speaking, in terms of just getting power from point A to point B, doesn't matter what frequency you use. And this is true for the transmitter too. If I have a fixed amount of area to transmit in, and I have the freedom to point it to my receiver, and my receiver is an omnidirectional receiver, well, something that has a G of R of 1, then again, that link becomes frequency independent for the exact same reason. I could have just said, I'm going to use the electromagnetic area of the transmitter instead of the receiver. Same dependencies fall out. So that begs the question then, what if I have two apertures? I have a fixed amount of area at my transmitter and a fixed amount of area at my receiver. And I want to exchange power, and I have the freedom to point both of those. So what I'm doing is I'm going to take this equation that I got here. Let me clean it up for you. PT GT over 4 pi r squared AEM. Now let me take the electromagnetic aperture, effective aperture of my transmit antenna. It's not going to be electrically small anymore. It's going to be 4 pi AEM, and let's call it AEM comma T, AEM comma R, to denote that they're two different apertures. And this is 4 pi r squared. Oh, and there should be a lambda squared in the denominator again. 4 pi's cancel, and what I'm left with is 4 pt over r squared lambda squared times my two apertures. So remember, I only get electromagnetic aperture is like proportional effectively to my physical aperture of my antenna. But it means I have to point it. I only get that maximum electromagnetic aperture if I point the physical aperture towards the radiation, gather all the energy, and it's being excited by a wave in such a way that you get constructive interference across that aperture at the terminals of the antenna. Like a dish antenna. Think of a dish, parabolic dish reflector. Well, so now what's the benefit? Should I use higher frequency or lower frequency for this? Higher. That's right. And now it's completely the opposite of what we started with. And this kind of, in a way, explains why we choose different frequencies for different applications, right? So when we're broadcasting radio, let's say we're broadcasting FM radio or AM radio, or even VHF television. That's a broadcast to an omnidirectional user, and it's beneficial to use low frequencies for that. So that's why we use low frequencies for those applications. Aside from the fact that it was also, as a point of legacy, it was easier to build electronics at those lower frequencies. There's still a big demand for those low frequencies because they propagate so far, and it's very easy to build these broadcast applications for that. So then you go up, and now you're at the upper UHF band and the lower microwave frequency regime. What do we use those frequencies for? We use them for what? Cellular communications, right? Cellular communications, it's probably a little closer to the second scenario that we talked about rather than the first. And the reason is how we divide spectrum. Your handset is a low gain antenna, and it has to be because it's got to receive from every direction. However, the way that we partition spectrum at base stations and in the city that we're covering, you get a certain amount of spectrum as a cellular radio provider. And if you're a good cellular radio provider, you're going to reuse that spectrum. Because in the United States, we got to pay for it. They auction it off. The government auctions it off. The highest bidder pays for it. So the highest bidder better figure out how to reuse the same frequencies again and again throughout the city so you can get the most data, the most customers, and ultimately the most revenue through your cellular network. And so our antennas at the base station, they get gain in this direction. They kind of squash the beam down. They elongate physically in this direction to squash the beam down in this direction. And then they also focus into sectors. So it kind of resembles this case where you've got a directional antenna that you can point in a certain direction. And so it's a little bit closer to scenario number 2 than is scenario number 1. Well, that means that the system becomes somewhat frequency independent. It's not nearly as frequency dependent as low frequency broadcasting. There are other conditions too that drive it up in that frequency. The fact that there's a lot of congestion down there at the low frequencies where everybody wants to broadcast stuff. So, you know, in the US, 700 megahertz is about the lowest band you could go down and use cellular frequencies. It's more common for them to extend up to 800 or 1900, or, you know, you can go higher. People are now talking about these 5G systems, next generation cellular, where you use millimeter waves. And at first, all the classical RF guys were, whoa, that's too lossy. I know what the first free space, that lambda squared is in the numerator, not the denominator. And it's true, it's a very lossy way to transmit things if you're doing broadcast to broadcast. But if you have the ability to focus, and you could have multiple antennas at your receiver that you can steer, then you can make up for some of those losses. So there are other issues using higher frequencies for mobile radio, but in terms of just pure path loss, if you have the freedom to point something, mobile radio is actually somewhat independent of frequency in its loss characterization. Now you go to this scenario where you have two directional antennas, you point them. What type of communications uses that commonly? Oh, this is satellite communications. Who was using millimeter waves long before it was cool to talk about in the cellular world? They've been using millimeter waves for decades in the satellite industry, because if you want to overcome tens of thousands of kilometers of path loss just to get to an Earth-based satellite out in geostationary Earth orbit, or even worse, if you're sending a radio wave millions of miles to talk to a rover on Mars, or a spacecraft on Saturn, or Voyager, which has left the solar system completely, at least the inner planets, all of the known planets that we talk about. You know, in order to overcome the enormous amount of path loss, you would like to have two directional antennas that you can point. And once you have that, it's actually better to go up in frequency. Makes it harder to point. Beam widths become very, very small, and it's a challenge to get the thing to point back towards the Earth. But we can do it. And it becomes a mechanical controls problem, not our problem, right? Mm-hmm. So anyway, that in a nutshell is how these systems behave. So then to summarize with the radar equation, what you find is some of these exact same trade-offs in that second form of the equation that I put on the board. PR is equal to PT. G transmit, G receive, lambda squared, sigma RCS over 64 pi cubed r squared. Oftentimes, if this is a true monostatic link, this is the same antenna, which means you can write this as GR squared or GT squared. And you see there's some of the same issues at work here. Generally speaking, there's a lambda squared in the numerator, which means there's 1 over frequency squared dependence in the denominator. You're going to get a lossier system. However, you can make up for that and even turn the high frequency from a liability to a benefit by moving to a directional antenna at points. And in fact, you see, if this is a GR squared or a GT squared, you're in a monostatic radar link. I know which direction I want to listen to because it's the same direction I transmitted from. So I could get 1 over lambda to the 4th by adding a directional antenna, and that will easily overcome that additional lambda squared loss in the link. So I see some of the same principles at work, right? And this explains why radars tend to operate at really high frequencies. Maritime radars tend to be around 8 gigahertz, higher than you would do cellular communications, because you have the freedom to point both the transmitter and the receiver. And of course, there's all the different military and aviation radars out there that generally inhabit the microwave or millimeter wave spectrum. Okay, now we have about 15 minutes left by my account. So let's talk about the last link budget equation. And this is the backscatter link budget. So in this scenario, what we do say transmitter, receiver, separated by, instead of an object, let's replace that object with a tag that has load modulation. This is an antenna and some tag that switches back and forth two different electrical loads. Now we'll spend a whole unit talking about this form of communications later in the class, but I want to introduce it now because we're doing link budgets and we're kind of fresh with that concept. So we'll go ahead and just sketch what this looks like now, and then talk about some details about this later on in the course, because this is actually a very interesting way to transmit low-powered information. Okay. So in this case, we can actually start by using the radar link budget. In fact, this is how a common way of dealing with it. One of the things about radio engineers is that they have a way, they like to try to do new things by shoehorning it into the old way of thinking into things, right? So for example, in the 70s, whenever every research engineer was working in satellite communications into the early 80s, they're like, this was a great field. You've got an uplink to the satellite and a downlink from the satellite to the user, to the Earth station. And that's how they talked about communications. Well, now, all of a sudden, late 80s come around. What's the big radio application? Cellular communications. That people were making base stations and talking to mobiles. And how do you think about a way? Well, the natural way to think about base stations to an RF engineer at that time was, oh yeah, a base station is like a satellite on a stick, right? So they use the same terminology. Uplink to the base station, downlink to the user terminal. And so you see a lot of that same language that is kind of carried over into the next hot topic, right? And so backscatter tags are no different. There was this big explosion of interest in the early 2000s, about 15 years ago, as this field was kind of just starting to come into being. Backscatter communications has been around for a while, but it's the first time it was really commercially used. And, you know, how do we think about backscatter communications? Oh, this kind of looks like radar. So let's just shoehorn our understanding into radar. So you start with the radar equation, which looks like this. I'm just going to assume that we've got two antennas with similar gain. In that direction. Lambda squared RCS. And it turns out that if this is an antenna instead of just an object, then its radar cross-section, it will reflect just like any other hunk of metal or object in space. But we can actually solve for its radar cross-section. It is a function of its gain So G little t is the tag antenna gain lambda squared, we know what that is. That's wavelength. 4 pi, we know what that is. And then these two terms here, A sub s, this is a phasor. This is the amplitude and phase of the structural component. So what do we mean by structural component? This is what would reflect back regardless of what you connect to the antenna, right? Because the antenna is a hunk of metal, it will reflect a structural component, just like a metal orb, a metal sphere will reflect a structural component, or a metal wire will reflect a structural component. Then there's another component that has an amplitude and phase. This is the gamma, and this is the modulatable component. This is the component that depends electrically on what you connect to the antenna. So it's like a reflection coefficient. It's a unitless number. It has an amplitude and phase. It can be complex. And if you want to figure out how to calculate it, you use this formula. Make sure I get the signs in all the right spots. It's Z sub L minus Z sub A complex conjugate over Z sub L plus Z sub A. So it looks kind of like a reflection coefficient. The only difference is there's a little complex conjugate up there. And we'll talk about where that comes from later, but you can think of it as a reflection coefficient. And you'll notice too that it's A sub s minus gamma. It's interesting. The theory for this actually came out of the days of stealthy aircraft back in the United States. You know, you have they have these stealthy aircraft, like the B-2 bomber, the F-117 fighter, where they've done a lot of electromagnetic simulations to change the shape, and a lot of material engineering to change the composition, such that at certain frequencies these things are invisible to radar. Because I think they say that the stealth fighter had a radar cross section the size of a bumblebee, measured in centimeters squared instead of meters squared. For an aircraft that's bigger than this room, that's pretty. A lot of engineering went into that to make that happen. The problem is you would like to be able to communicate with your airplane, right? You got to stick a dipole on it to receive, or some antenna on it to receive communications. Well, you just took your thing that had a radar cross section the size of a bumblebee, and you stuck an antenna on it. Even if it's a small antenna, it turns into a basketball, right? So, one of the solutions, there's all sorts of crazy solutions to this problem. In order to keep your airplane invisible, one of the things they looked at was, okay, let's introduce an intentional mismatch to the communications link, right? It means our communications link won't behave quite as efficiently as it should. We'll still be able to use it. Maybe the range will lose a couple hundred meters or kilometer off there. But if we pick the right electrical mismatch here, that amplitude and phase will cancel out the structural component, and it will make the antenna disappear. And that's how the original formalized formulation of backscatter came about. They're trying to make antennas disappear from radar. So you could put a bunch of them on an aircraft like you always do, communicate with an aircraft. Oh, yes.
That one is
Oh.
ZA or ZH.
Let's see.
The definition of the Python.
This one over here? This is ZA. Sorry, the pen went a little crazy. That should be ZA. It's a load impedance of what you connected to the antenna minus complex conjugate of the antenna impedance itself, divided by those same terms added.
How say in the denominator is no conjugate.
That's right. There's no conjugate. And to understand why that's the case, we'll talk about that a little bit later. But you see that this essentially behaves as a reflection coefficient. If I have two complex impedances, an antenna impedance and a load impedance, and they both have real positive resistances and whatever complex reactances, I'm always going to get something with magnitude less than or equal to 1. That may not be the case for A sub S. A sub S could conceivably have a magnitude greater than 1. There are some antennas out there, like dish antennas, whose structural component is so large you can't possibly tune it out with by electrically changing the feed elements impedance. Anyway. Now, the interesting thing is that equation by and of itself is not very helpful because it's not actually a static antenna that transmits information. It's switching between two loads that you can send back ones and zeros to a reader in a link. And so for that reason, people will also define something as differential RCF. Differential radar cross-section, which is lambda squared over 4 pi g sub t squared gamma sub A minus gamma sub B squared. Or modulatable RCS, differential RCS. So in this case, think of it as, I have an antenna, and I've got two terminals, two loads, Z sub A and Z sub B. And I just connect back and forth to each one. I didn't do a good job of illustrating that, but think of this as representing one level of logic and this one representing a 0 or some sort of back and forth. Well, it's really the difference between those states that I can hone in on. And that's actually going to constitute the power of my signal. And so this is what you put into the radar equation to calculate that third form of backscatter power. So probably by Wednesday, I'll give you a homework number 2. It'll be due before the Chinese New Year break the following Wednesday, and then you'll be relatively work-free for the class over the break. And you'll probably have some problems involving some link budgets of backscatter links and conventional links. Any questions? Well, thanks. That was good. We compressed an awful lot of link budget knowledge into one big lecture period. And we'll be back on Wednesday. And I think the topic there, we're going to talk about, get back to energy harvesting and talk about some electronics and some techniques to increase the range of an energy harvesting circuit. So you see how we're kind of building on the class here. We're figuring out how to get power from point A to point B and how to track it also in a reflective communication signal. Now that we can figure out how much power to get from point A to point B, we can track the circuit losses and the mismatch losses. And then we can figure out basically, okay, I got this much power. How much can this go end to end into this energy harvesting application? And thus, how much power will I have available? How much voltage will I have available if I want to hook a circuit to this antenna and do something with it in the far field? Okay. See you Wednesday.